Good morning all. Some new PCBs have arrived from JLCPCB. So let's take a look inside this box and have a look. And this time I went for red instead of the usual green. So what is this PCB for? Well, let me have a closer look at one. So on the top side we have two 3-pin connectors. This is input, this is output. We have some LEDs here, a resistor. Now we've got these two 4-pin dual inline packages, so you can probably deduce that those are opto-isolators. There's this odd thing here, this block with 4 pins down one side, and then there are a couple of resistors here. On the reverse side we've got an A23 battery holder. So what this is my DCOI, my dual complementary opto-isolator, MOSFET driver unit, finally immortalized on a printed circuit board. I have been building these on Veroboard, but there's a couple of reasons why I wanted to go to a PCB, and one of those is this, because this original version had a 9-volt battery. Well, I then realized that I could use this little Murata step-up DC to DC converter, steps up from 5 volts to 12 volts. It's isolated as well, so that you retain the isolation between the input and output side, if that's important. It isn't always. But actually, yes, in some instances it might be with the inductor-based circuit. And this all works rather well. So there are two options here. There's either a battery or a little step-up DC to DC converter. And on here I've decided to go for the A23 battery, which is one of these sort of cigarette lighter 12-volt batteries. So it's probably just a bunch of little 1.5-volt button cells stacked in a cylindrical package. But you can get a little holder for this thing with PCB pins. I thought I'd put that on the rear side, and then all the other components, the optos, this little DC to DC converter, which has these 4 pins on it, goes on this side. So really the battery and the DC to DC converter are alternate options. Now if you saw my latest Muppet video, you'll see that I used this and that, and they both seem to work fine. The other thing I did was I plugged a 9-volt battery onto here with the DC to DC converter in circuit, so that the 9 volts was just connected directly across the output of this thing, and it didn't seem to mind. So it'd probably be the case that if you put the 12-volt battery in here and you've also got the DC to DC converter in the circuit, that actually nothing bad is going to happen, probably. Now I have to say that this was the quickest printed circuit board that I've designed so far. I had no schematic, so I drew the schematic and then I laid the board out, and the whole process of schematic and PCB design was just about 2 hours, I think. So it was really quick. I don't have all the parts for this yet, so it's going to take a little bit longer to assemble it. In fact, I might even put through-hole LEDs in these positions here, just soldered on the surface of the board, because I don't have the surface mount ones yet. So I might make up a little bodge version as my first one and then build some more of these properly. One of the other reasons I went for this circuit board is because I know that for my bidirectional energy transfer I need 4 of these MOSFET drivers driving 4 MOSFETs. So to have 10 of these boards is really quite convenient. One of the reasons that this came together online so quickly is that most of these components were in the standard libraries, but this DC to DC converter I could only find in a user submitted library, but it was there. I don't think it was actually the 5 to 12 volt one. I think it was 6 volts or something, but it didn't really matter because the pinout was the same, so I used that. Some user had also very kindly submitted the footprint for the A23 battery holder. Now I have ordered some of those holders, they haven't come in yet, so I'm not entirely sure that this pitch is correct yet. So I've taken a little bit of a flyer on that. But anyway, let's go online to Easy EDA and just have a quick look at my schematic and my PCB layout for this. So this is the schematic for the DCOI MOSFET driver. You can see the 4 LEDs, the red ones and the infrared ones, in the opto-isolators in this long series string. So they don't light up when you've got 5 volts across them, but they do if you pull this resistor, 220 ohms, either to 5 volts or to ground. On the output, I've put these two 10 meg resistors. That stops the MOSFET gate source voltage sort of creeping up when there's a battery in circuit. Here's the battery holder for the 12 volt A23 that sits across the two optos on the output. And here is the DC to DC converter. It's just called a DC-DC converter single output. I've put a 1 microfarad tantalum capacitor across the output of that because that's what the datasheet recommends. One of the other things I did was, of course, on the Veroboard version, this middle connection to the 220 ohm resistor was in the middle of the header pin. It was actually 4-pin header on that, but that meant swapping wires over. Let's have a quick look at that. Yeah, so on this one, VCC would be this grey wire coming through the 4 LEDs, and then the signal, which is connected to the resistor, is this middle pin, because that's just how it's best laid out on Veroboard, on strip board. But of course, when you come to put these 3 connections on the Arduino breakout board, the signal is to one side and then VCC is in the middle and ground's at the other end. So it just means bringing this center wire out and folding it over so that it, crossing it over so that it sits on the edge there, because that's the signal. So I made the decision on these boards to cross it over actually on the board, so you can see that R1 actually goes to that top pin, and then these other 2 pins go out to these 2 LEDs. Now I've just got to remember that I've done that because I've got quite used to having this crossed over 3-pin wire. I haven't done a crossover on the output side because there you've got a choice of either center and the positive connection to put the signal one way around, or you can invert that by going center and the negative connection. On here I've got a 4-pin connector and both these middle pins are effectively that center pin, but on here I've gone for a couple of 3-pin connectors. So I just thought I'd iron out a few of the little anomalies that were created by the Veroboard design. And then moving on to the PCB layout, this is a mixture. It's mostly through hole actually, with surface mount LEDs and a few resistors. And because there are so many through holes, this doesn't need any vias. I was able to route it all with top side tracks and bottom side tracks. The color coding here, of course, is top side, bottom side, and the silk layers. But let's use this camera and the new 3D view. Now this is terribly slow on my PC, and with OBS running as well, I'm going to have to do this and cut because it just takes forever. But we can actually see when it comes up a 3-dimensional view of the PCB. Oh, there it is. Right, now if I rotate my mouse wheel, it will very slowly... Oh, that's really slow. I'll have to cut the shot. So this 3D view lets you see the board as a sort of finished board with the silkscreen, the tracks, the tinning. As I say, it's very slow to render on my PC. And of course, this one shows it in green, but I can also come up here and select other colors. So let's have a look at the color I chose, which is red. So here is the rendering for red. It's not entirely accurate because you've got this sort of funny yellow edge, which actually doesn't show on my board. It's a red edge. Let's just have a quick look at some of the other colors available. So here's purple, which was the color made popular by Osh Park, but you see a lot of little modules on purple PCBs these days. Yellow is an interesting color choice. I'm not sure I've ever seen a yellow PCB. Ah, wait a minute. Yes, I think I do have one. I'll try and find that in a moment. And here's white. which is becoming more common these days. And of course with white, the silk screening has to be all done in black, but yeah, that would be an interesting choice. Maybe I'll go for that next time. And yes, I knew I had a yellow PCB somewhere. It's this AD584 precision voltage reference, which you can use to calibrate your DVMs. But yeah, that's a yellow, by the look of it, double-sided PCB. Right, I think in here I've got some 220 ohm resistors, 270 ohm and 220 ohm. Okay, so I can fit the 220 ohm resistor there. Right, I think this tip is probably a tiny bit fat for what I'm doing, but it'll do. Bit of solder on there. Resistore goes there. Ooh, should get my positioning a bit more accurate than that. Like so. Press it down. Solder that end. Flip it round. Get my solder to... And there's the 220 ohm resistor on. Now I don't suppose you saw any of that because I need the headroom while I'm working the soldering iron. So let's zoom in and have a look. Well, it's not beautiful, but it'll do. Right, couple of opto-isolators. There's the pin 1 mark. Let's bang them in. And then I can fit my 2 LEDs, which, as I say, are going to have to be through-hole LEDs onto surface mount pads, which is not ideal. Right, let's get these optos on. They should be pretty quick because they're through-hole. So they solder really nice and easily. I think I chose the leaded board rather than the lead-free because, well, I'm using leaded solder. Now, because I've put the battery holder on the rear side, I'm going to have to crop off these leads pretty much flush with the underside of the board. And these aren't completely flush cutters. There's a little recess in there. So I'm not going to be able to get it quite flush. But then under this part of the battery holder, it should be just plastic. I'm just wondering actually whether there's some advantage in having it stab itself onto these legs. I'm going to cut them down a bit, sort of to anchor it in place. I don't know. Right, now I want to break off a couple of 3-pin header pin arrays, and I'm going to go for straight. On the Veroboard, I went for these angled ones, but on here, because I've got the battery holder pins outside of the pin header arrays, I don't really want to fold them over and then have difficulty soldering the battery holder in, because I probably can't get to it from that side. So I'm going to go for straight, which will work the same as this. The wires will come up out of the board and then loop back down over onto, and it'll mean that everything will be slightly more compactly placed on my desk anyway. So I'm not sure the right angle thing was such a brilliant idea. These are going to be straight. Right, let's get those soldered in. Iron's gone into standby, so let's let that warm up again. Right, solder these pin header arrays. These are going to be a bit harder to crop probably, aren't they? Well, maybe the battery holder will just sit on the top of these. Perhaps I don't need to crop these down. Also, the solder's not flowing down into the through hole quite as easily as it was with the opto-isolator. So yeah, they're not going to be able to be cropped off, I don't think. Right, next to go in will be the little Murata DC to DC converter. Pin 1 is marked with a dot, and it's also marked on my silk screen. Thank you to whoever contributed that particular item, because that's just a drop in. And a suitable capacitor. This is a 3.3 mic, but I don't think it really matters what I use. Positive is marked there. Oh, that does look quite nice. And yes, I have to say that that is looking quite nice with its little Murata NKE 05 5V to 12V step up isolated DC to DC converter, the two sharp PC817 optos. So I need my red LEDs, and as I say, I'm just going to use through holes on this one. I mean, I can take them off later and put the surface mount on. I have ordered them. The two 10 meg resistors there don't do a huge amount. They just protect the MOSFET from drifting up, which won't happen actually when I've got the DC to DC converter, because of course as soon as you remove the 5V, that 12V output will disappear and will come out of that cap relatively quickly, probably before the MOSFETs can drift up and switch on. You only really need those 10 meg resistors if you're using the battery option. When I get my battery holders, which I don't have yet, let's find a couple of red LEDs. So these two LEDs are going to be fun to get on because I've cut the legs quite short. So I need quite a bit of a blob of solder on these. And then I've got to kind of get in underneath them. That's going to be fun. So yeah, they're a bit temporary like, but that'll do until my red LEDs turn up. Right, let's put it on the Arduino and fire it up. So this is where I can now take off my 3-pin connector and put it on the actual 3 pins of this and not have to do my crossing over thing when I connect it onto the Arduino. I can actually have the 3 connections in the same sequence. Right, so I need to plug some juice into the Arduino. I probably should switch this iron off so I don't melt wires and stuff while I'm doing this. Right, let's see what happens if I plug this in and the lights come on. Should they both be on? Probably yes, if we've got a voltage floating about on A7 there, because I haven't got my pot on there yet, so perhaps I should get that on there. Yes, because of the last program I wrote into here only takes the pot to 2/3 of its travel. It starts at the bottom. Oh, that's got some funny business going on there. As we raise that up, it switches over to the on side and it completes the full sweep of PWM by about 2/3 of the range of travel. So the last bit doesn't actually do anything on this DCOI MOSFET driver. So yeah, that looks about right for the input side of this. Right, now this is all working fine. I turn the pot, the bulb varies in brightness as the PWM signal goes to the optos, but in my haste I made a tiny error. I actually didn't worry too much about the orientation of this output connector, and it's actually backwards. It's got negative at the top, positive at the bottom. It doesn't matter really at all, because as long as you connect the wires to the correct pins, and I'm just going to have to remember that the positive is at the bottom end, it all works fine. And it can work in inverting mode or non-inverting mode, so everything's good. But I just didn't think about where pin 1 and where pin 3 was on that connector, and they're actually the other way round to how I had it on the Veroboard version. But as I say, it doesn't really matter. I've just got to remember to connect it up that way round. Now if I get it wrong, all that happens is I put a negative voltage on the gate of that MOSFET, and that isn't a problem. MOSFETs don't mind up to about 20 volts positive or 20 volts negative. Of course, with a 20 volt negative voltage, it's not going to turn on. It won't go into enhancement mode. I keep hitting that ammeter. But yeah, that actually all works fine. And these boards are a lot quicker to assemble than the Veroboard versions were. So yes, I'm very happy with my new PCB. Yes, and I kind of know why this happened now. If you look at both these connectors, you've got pin 1, the square pin, at the bottom. Well, if I go to the schematic, when I drew this schematic, I pulled in this 3-pin header, and of course I copied the one on the left side to the right side, but I did a 180-degree rotation so that the pins, the wires were heading inwards. And that means that on this left one, pin 1 is at the bottom, and on the right one, pin 1 is at the top. Now, intuitively, I connected the top pin to positive, the bottom pin to negative, but these are different to how they actually physically are laid out on the PCB. That's how it happened. And as I say, it really doesn't matter. It just means remembering that the pin 1 is the most positive side. So yes, I've got boards enough now to make 4 MOSFET drivers for when I'm driving the 4 MOSFETs to do bidirectional energy transfer. And because I've only got 2 of these little Murata step-up converters, I'll probably buy 2 more. But probably what I'll do is I'll use step-up converters on 2 of these boards, and then the 12-volt A23 battery option on the other 2. Why not? So a really big thanks to JLCPCB for supplying these 10 DCOI MOSFET driver PCBs. I can now move my Muppet 2 project onto really the final phase, which is bidirectional energy transfer. Cheerio.